Today we're going to look at some biasing issues, but before we get rolling on that, I want to show you my little tone generator. Because I'm a cheap ass, I didn't want to buy one, so I found this on Amazon for 10 bucks. It was a kit. You just kind of solder the components onto the board and put it together. So anyway, I'm set up here. You plug a voltage source in there, anywhere between 9 and 12 volts. I have 12 volts on it. And I've got my scope hooked up. And that's what I use to inject a signal when I'm doing certain types of testing on amplifiers. So right now it's got 104 millivolts coming out, which is what I want. The frequency is not terribly critical. It's around 250. But I'll play around with the amplitude a little bit. That is... So we're up to 300 millivolts here, and maybe for certain things that might be useful, but for guitar amplifiers, you want to be around 100 millivolts. You can go a little lower, a little higher, but 100 is a good number to stick with. For example, the low string of a Stratocaster plucked pretty hard has put out about 50. So you take a humbucker and strum it across with a bar chord or something like that, and it'll put out close to 300. So I use 100, and so I got it set back to about 104, and that is my little tone generator. You can find it on Amazon. The first thing I want to look at is the plate characteristics on the 6V6 GT. This is a curve from JJ, which calls their GT 6V6S, but it's the same thing. A newer version of that, they'll take easily 450 plate volts. So the newer amplifier, especially the one that I built, has at least 400 volts on the plate. That's plate to cathode voltage. In fact, it's more than that in some cases. So this chart's going to show the plate current on one side, and across the bottom will be the plate voltage. And then that curve that cuts across the middle there, that is your plate dissipation, maximum plate dissipation. You really don't want to go over that. You just save the life of your tubes, and it gives you better overall performance. So anyway, our plate voltages are at least 400 volts, which means I have to draw that line up from 400 volts up to close to the plate dissipation line and then cut across, which means my plate current needs to be somewhere between 20 and 30 milliamps. Now that becomes an issue, and we'll get into that a little bit later. So for a lot of really good information, go to the Aiken Amplification website. He's got tons of really good information there. Everything to do with tube amplifiers. So I'll stop it here and read here. A general rule of thumb is that Class AB amplifiers are usually operated at no more than 70% of maximum plate dissipation of the tube to account for the higher dissipation that occurs under signal conditions. Now that is generally true with a fixed bias. We don't have a fixed bias, and after looking around, I kind of stumbled across this one day, and I hadn't seen it before. So it says here, cathode bias Class AB amps, push-pull, are usually exempt from the 70% rule because their cathode voltage rises when a signal is applied, effectively reducing the bias and shifting the amp further into AB operation. This means you can bias them hotter than a normal fixed bias Class AB amp, and the tubes will still survive. This information intrigued me because I have the 5E3 amplifier that I built, and I'm getting some kind of funny noises that I don't particularly care for. Now, I run very high plate voltages, well over 400 volts, and that can bring in some additional issues. To compensate for very high plate voltages, which is what I've got, you have to run much lower plate current to maintain the dissipation for that tube. Otherwise, you'll red plate it. Now, when you get the current down to a certain point, that brings in a problem. It's called crossover distortion. And it's really difficult to get rid of. So I thought about it, and I go, well, what about if I just go ahead and raise the dissipation rate that I'm running? Because I'm running at about 70% now. That's the way I set that amplifier up. And from what I just read here, I can run that hotter, which means I can bring up my plate current and get rid of some of that crossover distortion. So that brings us to the next part. So I have the chassis up on the bench, and you can see I've got 3 meters up there. The one on the right is going to be measuring my plate voltage. That's from plate to cathode. And the other two will be measuring plate current. And just those two numbers there will give you your dissipation. Now I also have a scope set up, and we'll be using that also in this. And a quick word on dissipation. That is the number that you are concerned with. The main concern is plate dissipation. Not plate current, not plate voltage, or grid voltage, or any of that. You can't concentrate on those things. What you need to have is all that information so you can derive what the plate dissipation is. So this is with the original setup I had. It was running around 70 to 75% on the plate dissipation, which is what I thought I had to have based on everything I knew, at least before I read that one section on Aiken's website. So I'm running at about 25 milliamps and 416 volts. So I'll let it settle down. And then we'll run those numbers on the calculator and see where our actual plate dissipation is. So let's run the numbers on here. I got to keep reminding myself to not get the camera too close because it doesn't focus well very close. Anyway, so we have our plate voltage at 416, and you multiply that times the actual amps, not the milliamps. So that would be 0.025, and we get our plate dissipation at 10.4. Now I'm going to convert that into the percentage of the total, which these tubes will handle 14 watts, and it'll tell us what percentage of that we're currently at. It should be somewhere between 70 and 75. So we're going to have 10.4 divided by 14, which will give us 74%. So that's where we're at. Now what I want to do is take a look at the waveform at these settings, at this biasing level. So we'll use the scope here, and I'll increase the voltage or the volume until we start getting signal. And then we're starting to get some signal. And as I increase, you're going to notice that little hump in the middle of the waveform. Sitting a little over 2 on the volume. You'll notice a little hump as I increase, and that is crossover distortion, which is happening right there. Now you'll notice I'm also at about 9.2 RMS volts at the speaker. So that crossover distortion happening there is not good. It's happening, it's not good. So here I'm looking at our plate dissipation to make sure it's still in line, and it is. Cathode biasing is somewhat self-regulating in that regard. So I'm going to go ahead and run it up till we start clipping, and the crossover distortion gets much worse. So as I run it up, you're not going to see a big increase in the output. So there's the clipping, and then you see the crossover distortion. It looks like 2 shelves right there in the middle. But we're still getting a little less than 10 volts. And when you run that number, basically I'm getting less than 10 watts of output. So you take that 10 volts, you square it, and you divide it by the resistance at your speaker, which is 10 ohms. So that gives you about 10 watts of output power. This amplifier is capable of much more than that. Plus I've got that early breakup and that crossover distortion, which I don't really want. It's not good. You really don't want crossover distortion. So I lowered the value of that resistor, and we're ready to go again. I'm hoping to get the biasing up closer to its capacity of 14. So there's our plate voltage, and there is our plate current. You can see it's quite a bit higher, and the voltage is lower, which is normal. So we're running at about 408, 409 on the voltage, and I'm going to let this settle in at about, we'll kind of call it 33 milliamps, and run those numbers and see where we are. So we'll plug in our numbers, 409 volts, 0.033, and that gives us 13.5 watts of dissipation, which is under 14, but just under. So that's what I was looking for. Now what I'm going to do is start looking at the waveform, and we're going to see what's changed. So let me start to increase the volume a little bit until we get a wave. There we go. And you're going to notice that we don't get the crossover distortion until we get a significant voltage on the output. So we don't have, there we go. Right in here, you'll begin to see a slight amount. Not very much. But we're at 11 volts now, which is significantly higher. When you run the numbers, you'll see, which is quite a bit higher. And the crossover isn't so abrupt. It's slight at this point. So we're looking at our volume control there. It's a little over 3. That's one of the characteristics of this 5E3 is that you start breaking up early on these amps. So we're at probably our peak clean there, which is, right about 11.2 volts. We can squeeze some more. We get it up. We start to square wave there, start to clip at about 11.4. You can see my clipping is asymmetrical, which actually is a good thing. I got to get it up quite a bit before I start clipping on both sides of that. But you can see that the crossover distortion, even up in that range, is not as bad as it was. But we've got significantly higher output. Now, I won't know what all this does yet, because I'm going to get the amplifier back together, and I'm going to test it out, and I want to hear it. So let's run some of those numbers and see what we're getting. Got to get the camera too close again. So I'm going to use, let's see. I'm getting 12 watts of output at that particular point, but that isn't the highest output. I can get it up a little higher. It gets into a little farther into the clipping range, and it'll go up a little bit. So peak is about 11.4 volts, and if you run those numbers, I end up at roughly 13 watts of output, and that's significantly higher than the less than 10 I was getting at the other biasing, plus it's cleaner. So we'll find out what it sounds like, although probably not in this video. I'll have to do another video for that. And the other thing I want to check is, at that level, what is my plate dissipation? Is the cathode biasing doing its job and keeping us from red plating? So I look at the numbers. We're running 400 volts. And I'm going to call it 32, the average between the two of 32 milliamps. And we'll see what those numbers generate. And it's going to end up being below the 14, which is 12.8, so that's good. So at least what I've learned from this is that if you have a cathode biased push-pull amplifier, like the 5E3, and there's probably not very many other than the 5E3, you're not married to that 70% biasing rule. In fact, it may not be that good for it. You may be better off running that biasing up there closer to the actual capacity of those tubes. So anyway, thanks for watching, and I hope this was some useful information for you.